so going back to it. So today it's going to be about inversion interpretation. There's two big modules, and I'm going to start from scratch just to remind you guys how to do certain things, but we'll go focus in these two modules. So the first, I'm going to do some initial setup, just identify the logs of interest that we have, visualizing them, loading the data, detecting, and then we're going to detect boundaries. So we're going to move a little bit towards analysis. After we have detected the boundaries, we're going to move into the MCMC module. That is a module that allows you to interpret petrophysical properties independently. We're going to do an overview, and then we're going to see how some of the new things that we've done, in particular the borehole corrections that can be useful, and the adjustment of bed boundaries that has been working fine lately. And then the last part is going to be the compositional joint inversion. This module in particular, I'm interested in listening to your comments and suggestions. It's a state-of-the-art module that has some, basically it's undergoing the development. It's already working, it gives you results, but we know it can be improved, and we want to listen from your suggestions. So I'm going to start with the I opened UTAPWeLS. I have the project set up, but I'm going to start from a new well. I'm just going to load some data. We're going to start from, like I said, we're going to start from the beginning. And then I'm going to take a shortcut and go a little further. So right now I'm just loading data. It's warning me that there's two logs that have the same name, and to make sure that we can get them, it's just telling me that they need to be separate. So now this is the well interpreter for this well. And we can see here the gamma ray got loaded in immediately. And the first thing that I'm going to do is I'm just going to plot the density. So here I go to LAS, and now we have the density plot. The limits, of course, don't look too good, so I'm just going to make them make sense, just sandstone units. And then I'm going to focus in the area that I'm actually interested in. So here you right-click, and this little modification we made, now we have set reference track limits. So you can have data anywhere, and you can set the limits of the reference track to whatever you want. Before it was always the entire data interval. So I'm going to be interested in just the area from 3000 to 3030. And now you see the gamma ray and the density are in the areas that we're interested on. By the way, also the reference track you can modify. Right now it's got the limits from 0 to 300. That's probably a little much. So 0 to 200 is showing a little more contrast, is looking a little more interesting.
Are you double clicking these tracks to get the track editor up?
Yeah, you can double click on the track, and it opens the track editor.
Okay.
Yeah, also it's good that you ask those kind of questions, because I want to show you little tricks that we always do and can make your user experience a lot better. So besides just double clicking on it, you can also double click in the specific plot. For example, if I want to edit the boundaries, it opens, and it opens just in the boundaries that I want to modify. And then I'm going to add another one, and some other thing that you can do is just drag. With a right click, it will duplicate. If you do it with left click, it just moves it from one to the other. And then besides density, I want to show gamma ray. And I'm going to make it green. And 0 to, well, you can do a reset for the limits. If data is not showing, but 0 to 200 might be good. And that's it. Well, so now the last plot that I want to add is going to be resistivity. So I'm just going to do one more, and I'm going to add the boundaries. I'm going to leave them there, and then not from the Earth model, but from the LIS, we're going to look at the deep resistivity, RDeep. And of course, it's always better to visualize it in logarithmic scale. And this looks okay. Now, something that I wanted to show you user interface wise is how now we have this plot, and we have all this is associated to a template. This template is called default, but you can switch. These are some templates I've done before, but you can switch to any of the others, or you can add. So I'm going to make a new template. If you make a new template, that template is based on whatever you have. So it's going to make a new template that is exactly what I had. And you can make a new clean template. I'm going to make a new clean template. And even the limits are outside. So I'm going back in here. I'm going to set the reference track limits to the area that we're interested in. And this one, for example, I'm going to be just interested in density. So I'm just going to plot density. And I'm going to give it the right limits. Now, now I have template 2 and I have template 1. So I can switch between those two visualizations. That makes it a lot easier. We had this for about 6 months, 7 months, but I think it's worth revisiting just to show you. And I can rename them. For example, this template 2, it's just for density, so I can just call it density. This template 1 is the main, so I can just give it a name, and it's probably more illustrative of what they mean. And if I click in this save update in user settings, it's just going to save it in the computer. And if I click here, it's gonna show a check here. So that's why the triple combo and the fluid flow have it, because I've done that before. And you can revert to the last you saved. You can delete whatever. Now back to the inversion part that we're more interested on. So we're going to use the density log to detect boundaries. That's the first thing we're going to do. So this is the module that we've had for a very long time. We've improved it a little. We've given some help here. We added some comments, and we revisited the modules. That we made the window. We modified the definition of window now because it was twice what it is. So this is the definition. And then there were some issues with the second difference. Now we don't have those issues, so it works pretty well. Anyway, I'm just going to detect boundaries. But actually, the modeling interval that I'm interested in is a little smaller. I want to go to 30-30. Sorry, 30-30 to 30-40. That's the modeling interval that I'm interested in. So I can just go. This is it. And I'm going to detect boundaries again. And now it looks okay. So just using the maximum variance, we can see that it's making a decent job. There might be some issues here, but overall it seems to be doing okay. Now, the next thing we're going to do is we're going to actually try to invert for density. Remember, this is the field log that we have. And besides the field log in UTAPWeLS, we always have the Earth model. So we have the Earth model bulk density. So there's a property that is that corresponds to this field log. So in this case is density. It's called bulk density. Now to make sure that they're comparable, we have to make the limits the same. And something we can do is we can just right click in the log that has the limits that we want to use and just snap, and both of them will have the same limits. So now the bulk density is completely flat. I can play with it, remember? And what I'm going to do is I'm going to run just one forward simulation for the nuclear logs, including gamma ray and density. I'm going to make the step size is not a whole foot, but it's half a foot. Then I know the borehole diameter in this case is 12.25 inches, so I can modify that. It's fresh water. This is right salinity. I don't care about the mud cake. Sandstone is fine. It's not deviated, so I don't care about this. We're going to gamma ray and density, and it was LWD. So I'm just going to simulate, and I'm going to plot the density results. Simulated density, row alpha is what should match. I'm going to make it dashed just so that it's closer. And of course, it's very far away from the simulated log because, from the field log because, well, we never gave it any information for it to match. So we're going to go into the MCMC inversion module. Now it's going to get a little more interesting. We're going to try to, what we're going to try to do here is basically match the field log to the simulated log. So we're going to try to match the dashed line and the solid line. And to do that, we're going to get the right values for density, for the blocky log for density. So the property we're going to invert for is bulk density. It has a minimum and maximum. It's okay. If you had some core data, you could fix it only in those points, but we're not going to do that. We're going to use a Longhorn wireline, and we're going to make sure that the settings are right. So again, I'm going to make this half a foot, and it was 12.25 inches. Water-based mount, everything seems okay. And I'm going to try to match row alpha to the density log. Here it's going to give you the option of all the logs that the simulation is going to generate. And here is the field logs that you have. So it's going to simulate logs and match logs. And right now it only has one weight. We would have the possibility of having multiple. This is very common, for example, in resistivity. You could try to match multiple resistivity logs simultaneously, but in this case, just one is enough. Then it's going to auto-update the Earth model. So we're going to see it working live and update the simulated log set. And we're going to use the biased method. And there's two. We have the quasi-Newton and the bias sampling. We're just going to use the bias sampling right now. I'm going to let it run. And as it runs, I'm going to speak a little more about this part. And we're going to see that slowly, but surely it's going to get closer to it. It overshot.
You need to adjust the scales for simulated logs.
What is it?
You need to adjust the scales for simulated logs.
Yeah, the range for the
scale
for the simulated.
LWD.
Oh yeah.
Okay.
The range for
the scale, the plot scale.
Oh yeah, I see. Okay, so now it's working. Yeah, so now you can see that it's actually close to each other. Sorry. Now that we've actually gotten closer, I'm going to show you, well, the first thing is one of the modifications that we've done in this module is that we have now an accelerated search. So we can say that is the algorithm is going to be divided in two parts. First is going to try to find the minimum as fast as possible. And the second part is going to try to calculate the uncertainty. If the only thing you're interested in is just the single value, you can just do only accelerated search, and that's good enough. We're going to do that. We're going to allow it to run a little more, but we also want it to adjust bed boundaries because the bed boundaries may take a little longer. So I'm going to say at least 30 iterations, or the RMSD, it's going to very fast reach 3. So I'm just going to say, or if the RMSD is 1 or less than 1, it's going to switch. It's going to transition from accelerated search to out of it, which still searching, but a little slower. And it's, however, it gets better at calculating the uncertainty. The noise for density is going to be important in any case, but it's more important for if you're calculating uncertainty. And we're going to assume that it's 0.015 grams per centimeter cube. We also can use fraction or fraction plus absolute. So for example, for resistivity logs, you could just, it would mean that you have, in this case, 0.03% plus 0.15. resistivity is the resistivity tools are a little more common to have this case. Then the random perturbation 0.2 is usually fine. And the maximum, well, the total iteration is going to be 100. There's no maximum. This is the total iterations. I'm going to let it run. And we're going to see that at some point, the boundaries are going to be modified. And what we're saying is that because density is one of the higher resolution logs, we're going to trust that whatever modification we have, whatever it chooses as the final boundaries is correct. There was some transition already. I don't know if you noticed it, but you can see that there was a drop in the misfit. There was a drop in the RMSD. There was another modification. I'm going to show you how it's easier to see them in a bit, but we already see that they've improved a little. And we're going to see that after 30 iterations, the mean uncertainty is going to jump up. Right now it's been increasing. The way to tell if the uncertainty is already calculated properly is if it stabilizes, meaning it stops growing. Here it probably got a little stable, but not completely. Then at this point where you can see the transition here is going a little faster, it's out of the accelerated surge, and it's going to shoot up. And it's going to stabilize somewhere around what we originally gave it. It doesn't need to be exactly that. It may go higher, but it's okay. It's okay. And then sometimes it goes back down. That's okay too.
Joaquin, I have a question. So here you're inverting for the values of the density, the Earth model, and for the bed boundary location simultaneously.
Exactly. So both of them are being inverted for. That's right. And on top of that, the standard deviation too, which you can see how it behaves over here.
Joaquin?
Okay.
Cesar?
In this case, basically, you are assuming the matrix is pure sandstone with only water. So basically what you are changing in the Earth model is the porosity, I guess?
No. So at this point, we're going to get to that point in the next step when we do the joint inversion. At this point, we're doing independent inversion of the different logs. We're just trying to say, okay, instead of using the density as a continuous log or getting the middle point of the logs or whatever, we're going to try to get as realistic as possible, relying on the forward simulator. So we're getting these values, the exact values of the density in these positions. And then we're just assuming that that's the density. Then we're gonna combine density and gamma ray, and we can use PEF, whatever, resistivity to combine them into doing the actual petrophysical interpretation. But that's gonna be after we have already inverted for each of these independently.
Oh, okay.
So we're making it basically a two-step process, and we've tried it multiple times, and it really seems to be the best way to go. Just first clean. The way Carlos describes this part is we're getting rid of any tool effects. You may have this part done LWD or wireline, and then if you turn it into the Earth model, you don't care. You're just, it's the Earth model. So it's one of the benefits that we have. Could be multiple runs, could be whatever.
I see.
Yep.
Joaquin? Which version of UTAP will allow the MCMC and the inversion?
I think MCMC has been around for a while, but this one is the latest one, is 82. Roger can put the, because Roger can put the link in the chat. But the very similar version is since 70, I think. So this part has been there for a while, but there's been some improvements, some recent improvements. So for example, the Warhol correction is new, the fraction plus absolute is new, and some things that you don't see, but in the back end that make it more reliable and make it a little faster are also new.
Okay.
So Roger will post it in the chat.
Okay, thank you.
And you can ask for it, but it's out there. So at this point, we inverted for the value of the density and the standard deviation. We can also see it as confidence interval, and they're slightly different. You can see that the difference is that standard deviation is always going to be symmetric. It's just given the sample, all the samples that you have, just calculate the standard deviation using the standard formula. So basically, we're assuming that there's a Gaussian distribution around it. And the confidence interval is just ignoring that. And you can play with it. You can make it 90%, of course, makes it larger. You can make it 80%, whatever you think it's closer to what you need. And of course, it's not necessarily symmetric. So for example, you can see interesting things like over here, it's assuming that it's more likely to be below the value than if you use the standard.
Oh.
Joaquin, when you want to obtain the standard deviation, where do you define the noise added to the?
If you want to modify, you define it here, and we're going to do something else. So you, for example, right now we said it's the noise is absolute at 0.015 grams per centimeter squared. For example, we could say, well, what happens if it's 0.02, and you just modify it, and you can just hit recalculate, and it shows you how it would grow. Something else that we want to do is, I'm going to give it back to 0.15, and we have the borehole corrections. What that does is, given certain logs, either the caliper or the density delta, assume that certain locations have higher noise, because you know that the measurements are less reliable. So, for example, I'm going to plot, and I need to load another file that has that part, which is, I'm loading that real quick, and I'm going to plot the caliper. So here in LAS, this other file has the caliper. You see it's completely off, but I can reset and it shows you a little better. It's from, and well, probably better to see it in inches. So that would be 11 to 12 to make it a little better. Well, you can also reset and makes it rounder numbers, but it's still a little too close. So I'm just going to make it 8 to 18. So it's something we're more used to it. So we can see it's not very problematic. It's not very problematic. However, I'm going to plot a shade.
Hello.
So I'm just making a plot that shows you the areas where, sorry, I'm muting people. It shows you the areas where the caliper is off from the drill bit size, the original drill bit size. In this case, there was some mud cake that built up in these areas. So if we say that, we're going to say that in areas where the derivative of the caliper using this, I mean, there's two methods, cutoff and linear. Cutoff just means that anything above what you say. So for example, 0.2 inches per square foot. And of course, this is very small, but just for illustrative purposes in this case, we're going to say that anywhere where there's more than 0.2, we're just going to say the noise is much larger. And we just see calculate again, and you see that the areas here where you have the differences, the changes in the mud cake, they grew a lot bigger than they were. If I uncheck it, you can look at here and I hit recalculate, you're going to see that they get smaller again. So whether you take it into account or not, it's going to show you that it's going to translate into the uncertainty for these locations. Now, any questions or comments regarding MCMC? We're going to move into the joint inversion after this.
So Joaquin, just a small question. When you click on borehole correction and you recalculate the noise, what noise are we assuming then, if we're not assuming the 0.015?
So we're not assuming, we're assuming the same noise, but we're actually assuming, we're assuming that there is no relationship whatsoever. So we're making the noise infinite, basically, for only those measurements.
Okay.
And if you, instead of making, the way we're doing that is we're just, the areas where you have a difference between those two, to calculate the uncertainty, you need to take the average and multiply them by the noise. What we're doing is we're multiplying them by 0 in those cases. So the difference between the field and the simulated in the areas where we're saying there are above the cutoff, we're just saying the difference is 0. It counts at 0. If instead of the cutoff we do the linear, we have a smoother transition, and we can make it we can start at 0.2 and let's say up to 0.6, and it's going to be at 0.2 it's going to be full weight, so it's going to be completely relevant, and at 0.6 is 0 relevant, and you can recalculate and you have an effect, but it's a much smaller effect than what we had before.
Okay.
Yep. Okay. So now that we've gone over the inversion, I have one where I've already done the inversion completely. So we have the results for bulk density, for gamma ray, and for resistivity. And you can see that in some cases, the difference between the measurements you would get using directly the resistivity and using the inverted property are very significant, and not just in resistivity, but in all other logs, there's areas where that happens. Now what we're going to do is we're going to look into the joint inversion. And what we're doing in this module, the first thing I want to do is make sure we all are in the same page, is we're going to choose some properties we're going to match. In this case, we have these 3. We have bulk density, gamma ray, and resistivity. We're going to try to match all 3 at the same time. Actually, let's make just 2 to make it a little faster, and we can see the final part. We're going to invert for these 2, relying on the uncertainty that we have calculated. You can do it either from Earth model if you already did it, or you can just type a number, an explicit number if you have a better idea, or if you didn't do the full inversion. But in our case, we're going to do from Earth model. Then they have a weight. For example, you see that bulk density is fine, but gamma ray needs to converge a little faster. You can make it give it a higher weight, and it'll bias the search towards it. And we're going to try to match this given a certain input model, let's say, or which is actually the outputs, because it's the inversion in this case, so it goes in the other direction. And it's just defined by the minerals that we have. We have the orthoclase, pyrite, quartz, siderite, and so on. All of them are listed here. You can have some of them in matrix, some of them in shale. Then you have the independent hydrocarbons. Then you have water. And then you have, we're also inverting for porosity, for shale volume, and grain density. And each one of them, we can either allow them to fluctuate completely. We can, if you check it here, it means that you're not going to use it. In our case, just to make it easier, I'm going to just use elite as shale and just 3 matrix. We're just going to assume that it's fully water saturated. Just in this case, we're going to do it. We can do it fully, but it takes too long for this case. And then each of these properties has a prior that you can edit. In this case, for example, is the orthoclase quartz. This we got from lithoscanner, and it's in volume fraction. So it's some information that you already have that is going to help us converge to a result, and not just a result, but a result that is going to make sense given the information that we already have from the field. You can modify this explicitly, just moving them like that. And you can overlay a histogram. Of course, it's a lot easier to do it through histograms. And you have to do it explicitly. One of the things that we're working on right now is getting this automated. That's a module that it's in the build, but for now, this is good enough. And now I want to show you a couple of slides. So, well, and for how this works. So usually what you want to do is, well, we have a target property. Let's say it's density, and we know that it's 2.1 grams per centimeter squared. And by some means, we propose a property. Let's say it's 2.3 grams per centimeter squared. This proposed property is related to the components that we have. Let's say we propose a volume of quartz, a porosity, water saturation, and so on. And when we calculate the density, it gives us this density. So in a standard program, you would have the target property and the proposed property. You would try to minimize the difference between those two. However, what we're going to do is, instead of saying that the target property is just one value, because we already calculated its uncertainty, we're going to say, well, it's actually a distribution, and we're not going to try to just get difference between these two, but we're going to try to maximize the property of the proposed property in relationship to this probability distribution. Now, keep in mind that this is an oversimplification of what we have. This is just one property, and we're trying to match multiple properties. It's only interesting if you're going to do it with multiple. If it's just, if we were going to be working with just one property, this would be good enough. So we're going to do this, and not only that, but keep in mind that the proposed property is not just one value. We're going to say that it is just one value, but we have a prior. So we're going to say that that property that we're proposing is more valid the closer it is to the prior that we have. So we're going to maximize the probability of the proposed with respect to the target property times the probability of the components given their priors. So, well, and keep in mind that it's multiple components and multiple properties. Again, this is an oversimplification. We're seeing it in one dimension, but in reality it's 6, 7 dimension, but the brain is not really good at that. So it's better to see it in 1D. Now that we've done that, we're gonna try to match these properties with this composition. And I'm gonna start running it, and I'm gonna continue explaining what else we're looking at. When you start running it, you're gonna see that this plot is going to pop up. This plot is just showing us where restivity looks like it's matching perfectly, but it's fake. So we're just gonna get rid of it because we're not inverting for it right now. It's going to show you in the very left is going to show you the elements that you have. So in this case, orth case, pyrite, so on. Then, well, and we've modified this also visually. All the matrix are in the yellow-orange palette. Then the shale is going to be in a brown palette, and then the water is blue. And then you're going to see that, well, you're going to get a plot for each of the properties that you're trying to match. So in this case, you have density over here, and you have gamma ray over here. And each of those are, we're proposing a different set of components at every step. And that set of components is trying to get closer in each of the layers independently. By the way, that's important to say that each layer works independently. So for example, if you already matched a few layers, you don't have to worry about them later. And we can see that, for example, this one is already pretty close. This is a almost perfect match, but the density is still not doing fine. And some are a little harder. This one is not doing the best job, but given enough time, it will match. And yeah, so some of the newer things that we have here is, well, here in the settings, you can decide where you want to start. It's usually a good idea to do the first iteration starting from the most likely and then go into the current Earth model if you already are closer to what you think is the final answer. If you're going to start it again, so we could stop it and start again and it would not have an issue. Maximum iterations, then the misfit, at some point 3 is going to be too high, but 3 might be good enough to stop. Auto update Earth model, so we see how it's working real time. And we can see, well, and this is just to auto open the diagnosis plots, which is this track display. And then the last thing that we've been doing is we've been working with the optimization settings that we have. And if you remember from the slide that I showed you, you have 2 properties that are, or 2 probabilities that we're trying to maximize. One is the property match, and the other one is the output priors, the priors for the components. If you give them the same weight, they're going to have the same priority, and we're going to get to as close as possible. For taking both of them into account. In this case, because we have more outputs than inputs, we should be able to match it perfectly at some point. It already reached the 3%, so it stopped. We're gonna start again, but we're gonna say that the misfit, we want it to be lower. Let's make it 0 so that it never stops. And then we have a property match cost function. This is, again, we have help here if you forget how it works. So we have two cases. We have uncertainty weighted, which is the recommended. It takes into account the uncertainty that you have for the properties. And the downside of this one is that if you're really far away from the final answer, it takes a very long time to get there. And then at the same, we also have the property normalized that ignores the uncertainty, but it's a lot faster to converge. So probably at the beginning it was fine to use property normalized, but we're going to use uncertainty weighted at this point just to see if we can get closer. And we should get pretty close. So at this point, it's just a waiting game. You're gonna, of course, always help it if you see that obvious places where it's going in the wrong direction. The Android approach, just humans helping computers, is of course usually the best approach. And I don't know if there's any comments. We're in the 40 minutes mark, so it should be okay.
Yeah.
All the minerals that you define in the compositional palette are available in here, and with the same, I guess, endpoint values that you put in there, they will be the same taken here, I guess.
Yeah, that's a good question. Very important question. I should have mentioned that. There is all the minerals are defined in UTAPWeLS. We have it as a database. Here they are. And you have to make sure that you have the right properties, because we know that each field has its own, particularities, let's say. So you have to make sure that you have to make sure that you have the right property. So density needs to be correct and gamma ray properties need to be correct. Does that answer the question?
Yes. And can you open the prior for the quartz that you have here in this example?
Yeah, for sure.
So for example, in this case, you're telling that in this interval, you cannot have anything less than 40% of quartz, more or less? Is that what this is telling?
Right. Yeah, you're saying that is really unlikely. That is really unlikely.
Okay. I see.
You may find it in some cases. If that's the only way that it can do it, it's going to end up doing it, but it's going to take a long time to converge there. But yeah, and you have it's a Gaussian distribution, but you can also have a minimum and a maximum, and it can be by model. By the way, you could say it's not just one, but it's two. Well, while this is running, it's difficult to interact with this other window, but you can. Let me stop. Let's say that was good enough, and we can work with the priors. So now we have two. You can say, well, it's actually by model, and this one is slower than the other, or anything like that. Something else that is important in this case is that everything is working with rock in a rock class level. So, for example, if you have an iteration of sandstone and shale, you would need two rock classes. So you can add another rock class and give it a completely different definition with completely different priors. That can be very helpful.
Joaquin, I had a quick question. You're solving for, is it 5 minerals?
5 minerals, that's right.
With 2 inputs.
Right.
Okay.
Yeah, so in this case, you should be able to match it perfectly because you have more variables than outputs. Sorry, more variables than inputs. So you should be able to match it perfectly. I just stopped it because it was already just to keep playing with this. But yeah, you should be able to match it perfectly. And it's important to notice that you can match it perfectly, not just with one solution, but with many, many, many solutions. And that's why the priors are important, because it's going to make sure that your solution is making sense. You could match it with 0 quartz, for example, but is that good? No, we know that quartz should be within this distribution.
Like with the priors that you gave here, can you get a range of the possible solutions that we could come up with the same answer, for example, in this example?
I haven't done it, but I guess you could, yeah, why not?
I guess you would have to run it just multiple times, or how would you get a range of the possible?
To get multiple solutions?
Yeah.
Yeah, I mean, yeah, you could run it multiple times. It's going to look for the one that has the highest probability. So you should the one that it gives you should be fine. And the other thing that we're doing is we're moving in a direction where it's not just going to give you an answer, but it's going to give you a range of answers. So we're expecting them to be near each other. And similar to what we have here, for example, in gamma ray, you can see that similar to the standard deviation and the confidence interval that you could have, give a confidence interval for the amount of quartz or porosity. That's one of the things that we don't have it yet, but for sure that's one of the things that we're working on.
Okay, one question. First, thanks for showing this. This is a great product. For the shale, do you guys calculate a grain density for the shale, or do you work on dry or wet? Can you elaborate a little bit more about the shale volume?
The shale volume, we're just going to assume that is whatever you give it here, and the density is just going to be whatever you give it to the components that you have there. So we don't have explicitly a shale density prior. We do have a grain density prior that includes shale and matrix, and you can play with it right now. Well, for example, in this case, the grain density is not very informative. We just said very large sigma, very large standard deviation. So it's not really gonna matter in this case. But
so the grain density is for the whole class.
For the whole solids class, yes.
Okay, thanks.
Sure. Yeah. Well, and more questions. Also, I don't know if you guys would be willing to turn on your camera so we can take a picture.
I have a question.
But yeah, go ahead.
Thank you, Joaquin, for presenting an excellent inversion work. And is there any way that you can constrain like PIRES only exist from 3030 to 3035?
Which one?
Like specify one mineral on specific interval only. Like, is there any way you can constrain?
So what you would do in that case is work with the rock classes. So for example, you would just define certain areas to be a specific rock class, and the way you do that is you just go in here in the table. The easiest way to do it is in the table view. You can just say custom, and in custom you can do rock class, and in this case all of them are default. But if you know that in this interval are another type that has a specific mineral only, you can just say just class 1, and that would be much more shale heavy or something like that. That's how you would handle that. It's just use multiple rock classes.
Okay. And the second question is, you invert for the volume, right?
That's right.
And do you also provide the weight fraction?
The output is going to be in volume. We always work with volume, but it's not too difficult to convert, and people have asked for that. So maybe we want to start showing weight fractions too.
Okay, thank you.
Yep. Okay, so whomever can and is willing to show in the picture, let's turn on the cameras, and it's okay if you're in.
I think if you can see the weight fraction in the.
If you don't want to see, if you don't want to show up, it's okay. But
I think in the palette you can see the weight fraction, right?
In the palette you can see the weight fraction. That's right. Sorry.
So even right now, if you really wanted to see it for some layer, at least you could see it there.
Yeah, you could see the. That's right. You could in the palette. Yeah, thank you for reminding me. Well,
thank you, Bruce.
Yeah, here in the palette you can, and yeah, so it would not be too complicated to have the plots as also as volume fractions, but here you can choose if you want to see them as mass fraction, but it's only for the fluids though. It's only for the fluids, so we need to work on that. Anyway, so I'm gonna take the picture. Thank you all for being here, and it doesn't mean that we're stopping that. I'm trying to make this a little bigger. All right. Picture taken. Well, thank you. Okay.
Now I can breathe.
Now you can breathe, exactly.
So one quick question. I always love UTAPWeLS, and but the thing is that sometimes it's hard to use it because you have to change data between different platforms.
Right.
Is there any plans to kind of put this on the cloud so we can use it and using functions and an API key, so we can just whatever platform and an interface we're using, we just call it and do it in the platform that we already have?
Yeah, we've had that comment a few times. We don't have any, we haven't taken the time to actually plan for that. It's an option. I don't know if we're going to move to the cloud at some point. We need to think about it, to look into the actual possibilities and see how that's going to, the cost benefit. It becomes more of a business question than other, and see if, how long will it, we have 2 developers, and I don't know if it's something that would take, we need to take first like a week to see, to really see the options that we have, and if it's going to be something that's going to cost, let's say 2 months, maybe it's worth it. But if it's going to be something that is going to mean that in a whole year we're not going to have any other development, probably not. However, so the more you guys push for that, then the more likely we are to do it. So it's good that you bring it up, but I can't promise anything. What I can tell you now is that we have a plugin for TechLog that can be pretty useful. Roger can help you in getting it installed in TechLog, and it's a small user interface that allows you to say, just clicking, you have a project synchronized between the 2 programs, and you have this, they can see the same data, so you can export and import data from, well, logs and Earth model properties from UTAPWeLS to TechLog, and the other way around. That's what we have.
Are you talking about like having a central installation and then having a web access to it? Is that what you mean?
Yes. No. What I mean is that to be honest, I have a hard time to keep up with so many software that we have to install and things like that. So I install UTAPWeLS, and next year if I don't have it installed, I just don't use it. So I wonder if we can have it like an API key where, and you guys test the rights, the credentials to use it, but I just in the cloud, and from TechLog, you just call in a Python function, I need to do these versions, and I pass on the variables and then get back the results.
Joaquin, probably we can do that. This is Carlos. Probably we can do that. If that's the case, we just have to look at encrypting the data, because some of our sponsors are very worried about sharing the data and making sure that nobody else will see the data. But that's actually easier to implement what you're talking about.
Because what I mean, Carlos, and thanks for jumping in. It's like because you guys can check. Basically, it's going to be the data from the user, and you guys can certify whoever is trying to use it at the time has the rights to do it. So you can, as you mentioned, you can keep the privacy, and you can give access just to whoever is entitled to.
Okay, yeah. So let's, Joaquin, let's study that. We can encrypt and also do privacy keys for everyone, so that nobody sees anybody else's data.
Yeah, for the past year and a half, I think it's been a very recurrent suggestion. So I think we should take it seriously.
Yeah, but you know what they're talking about is not the plugin. They just want to access the software independent of their machine. Yes, and obviously they will be using the best, the most up-to-date software.
Yes, and we won't worry anymore about downloads and license, MATLAB. I mean, it will be on your side. Just you may have a kernel that just pass. We can pass a problem. Python is probably the easiest one, or whatever we want to use, and then we just get the results back, and it will be more easy to keep, to use it.
Yeah, web-based.
Yeah.
So it would be. I mean, there would have to be a central server that has it running continuously.
And I don't want to go on the weeds here because this conversation can go long and all. I just want to bring that up as a something that you guys can consider, and we'll be glad to discuss that further. You guys want to get some more on it.
That's a good idea. You know what I always tell Joaquin and Bruce and Roger is that what we need to have is more users. So if that is going to bring more users, we will do it.
Thanks, Joaquin, Carlos, and Bruce.
Just one quick comment, Joaquin. I really like this, like a quick presentation on updates on about UTAPWeLS. Are you planning on continuing doing this like on a monthly basis or regular basis? This is really nice.
Yeah, well, I'm glad you like it. Yeah, we are. The plan is to do it every 3 months, roughly. The next one, also, if you have suggestions about topics, it's a good idea. The next one we had planned is NMR. We've done a lot of stuff in that area, but if you have something else that you have in mind, that we can also talk about specifics.
Okay, great. Thank you.
Yeah.
How do we get a hold of the TechLog plugin?
Roger. Just send him he in the chat. He's sent already a link.
Yeah, it's easier. What easier to do? Just send me an email that you need it at UTAPWeLS.austin.utexas.
Yeah, you can probably put your.
I'll put that in but just send an email and I can send it out.
Okay. And actually, depending on how complex that is, a future version, a future one of these sessions could be related to that.
Yeah, that's a good idea.
Any plan to have a plugin with IP or not for now?
We have to explore the option. We need to talk to IP. What made the TechLog plugin easy is that they were very willing to work with us. So also, if you guys can talk to IP, that can also help.
I can suggest that. Okay.
Yeah. Okay. Well, thank you very much for attending, and I think we'll see you again in 3 months or so, or we'll keep shooting emails to each other and keep updated on the software.
Great. Thank you.
All right. Well,
thank you.
Thanks,
guys.